All right, this is gonna be my video for the 17th. Hopefully it'll upload quickly. All right, so I'm gonna go over, actually, sorry, let me turn this off. I'm gonna go over some of the same stuff I did the last time just because I kind of went through it quickly, which I'm also gonna go through it quickly this time, but just slightly different things. I just basically reread the what you need to know for test 3 document, and I'm going to try to cover all the little bits that I didn't cover. Of course, you should definitely read the slideshows that he's been posting. The last one he just posted today, Friday, is not on the test, I believe. It's not anywhere on the, I forgot what it was about, optical property or something. Anyway, it basically wasn't on the list of things you need to know because it wasn't about electric fields specifically so, or electromagnetic fields specifically so. Anyway, so I just want to talk about a few things. And so the first thing was just qualitatively, you should understand what an electromagnetic field, what a photon is doing. And I'm going to use the word photon. It just means electromagnetic wave. Sorry, electromagnetic wave. That's what I meant to say. And I told you last time, and obviously you know by now, that it has an electric field going like this, up and down, and magnetic field going sort of in and out of the board in this case, and then of course it's propagating to the right. But how do we know that? We can actually figure it out by using Maxwell's equations by using Maxwell's equations, we can see, well, let's say we just have let's say we just have an electric field oscillating. So this is just an electric wave, right? E. Now, and now the fact that the curl of E, that the cross product, well, actually, let me get to this later. I'm going to do this other thing first, which is that this, I'm going to use D now. Remember, D, of course, is just epsilon naught times E, right? Or epsilon times E if you're in some material. But this is just the charge enclosed. So actually, this is another thing. Last time I sort of, or a while ago, I didn't really make a distinction between the charge enclosed and the charge density here. And the reason for that is just because we're always going to integrate over all of space. We're not always going to. This is true. This statement is true. But when we use the other version that looks like this, Q enclosed over epsilon naught, I'm switching between D and E. Sorry, I don't, you can just do this all with D, and this would, let me do that actually. This goes away, and this is a D. So this is the other version of Maxwell's equation. This and this are the same exact thing, but we've integrated both sides over all of space. So if we do a integral over dv and an integral, I'm doing a triple integral because it's an integral over 3 dimensions of space. The integral of a charge density enclosed over all of space is just the charge enclosed. Sorry, not all of space, but all of the volume enclosed by the material, by the surface, I mean. And if we integrate this over all of this volume by the divergence theorem, we get this, the integral over the closed surface. So this Maxwell's equation, this one are the same thing. That was the point I was trying to make, but I didn't really distinguish between the charge density and the charge enclosed. The same exact thing is true for the current density, J, and the current enclosed, I. So J is the current density per volume, and for the same reason. And so for the other Maxwell's equation, you would do the triple integral and you use Stokes' theorem because you have a curl, and you can see why those are related. If you want to see those, you can go on Wikipedia. I'm not sure if they have a derivation of the relation between them, but they definitely have both of them listed. And they generally don't write things like Q enclosed on Wikipedia. They write this as 3 integrals of dv times rho enclosed, which is of course the same thing. And then I enclosed for the current, they would write as 3 integrals of dv over J enclosed. J is the current density. So anyway, sorry, that was a sidetrack. But so we have E, and we want to know what we want to know how what way this wave moves. Now, it seems like, well, oh, it's going this way, but we don't actually know that. What if it's going like out of the page? Like you could imagine a wave that's sort of oscillating in time, but also going in a different direction, like upward or something. How do we know it's actually, we know the answer. It's the answer, let me just write the answer up here just so we don't get confused, because I don't want to, you know, I don't want you to lose track of the actual true answer. When we derive this, we should keep this in mind, that this is what we should get. So if E is just an electric field like this, what direction is it traveling? Well, if we can write an electric field, we know from Maxwell's equations from the last video, we can write an electric field like this. Okay, this is just the solution to the wave equation, right? Now I'm going to use some different conventions, maybe in the notes or something, or in the slide PowerPoint or in the book or something. He uses R here. I'm just always going to use X vector, but X vector means X, Y, Z. I just use X because I think I like how it looks just like the one-dimensional version, because it is. It's exactly the one-dimensional version. It's just instead of having a one-dimensional wave kx, you have kx times x plus ky times y plus kz times z, where it's k sub x, k sub y, k sub z. But it's the same thing. It's just three, you know, this dot product is just, you can expand it out. But we're going to use this Maxwell's equation, and I don't want to keep switching between D and E, but in this case, it's just going to be much easier, especially when in a little bit, I'm going to get to boundary conditions where it's really actually very helpful to use D. I know I said before I liked E and B only, but I'm going to use H, and anyway, I'm going to use all those things. You should be very comfortable and write down somewhere on your sheet that you're bringing to the test the relation between E and D and then H and B. You should definitely write those all down. But I'm going to use this for now. It doesn't even matter because it's equal to 0. This is actually equal to the charge enclosed, of course, that I wrote before, charge density, okay, of some region. This is a local equation, so it's equal to charge density at some point, because this is a divergence that you evaluate at a point, right? It's a derivative. Derivatives you always evaluate at points, right? You can have an expression everywhere, I guess, but that would be just equal to, if you evaluate this at all points, that would be sort of an analytic expression for the charge density everywhere kind of thing. But normally you evaluate at a point. Anyway, the point is that there's no charges anywhere, so this is exactly 0. And because this is 0, we can write this as, let me make sure I'm getting this right. Oh, well, okay, it is actually going to be the same as this, of course, because epsilon naught is here, but we can just divide and it's 0. So it's equal to this. So this means that the divergence of E is 0, but the divergence, remember, is just the dot product of, and let's just look at the x direction. So this is the x component of del. This is called del, by the way. I think I said that before, but del, and we act on this. Now E naught is some, well, I'll leave it here. E naught is some vector, but then we have e to the I, and now we know that this, I'm going to expand this out. Kx is actually equal to kxx minus omega t. Now, of course, there's actually a plus. Let's just say it's going in the x direction or something. This is actually equal to kxx, you know, plus kyy plus kzz. Can you see this? Yeah, you can see this as long as I don't. Okay, good. And then it's equal to this, right? Plus, now it's the dot product of these derivatives, which is, so this is the x component of del, and then we have the y component of del, e to da, 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 plus the z component of del, e naught e to da, da. Okay, sorry, it's not really readable, but and the point is that each derivative, every derivative of x, of this thing up here, so the reason I only wrote x here is because this x derivative is only going to act on this x here, right? And it's going to bring down an ik. So when we do this, so let me write, I'm going to, even though I said let's keep this in mind, I'm going to erase it. I'm not going to erase this. The point is that this is going to equal, sorry. Let me write the other thing first. This right? And I'm getting rid of all the things. There's, of course, this is not the full thing. There's other components, and there's the t component. This doesn't, I'm just, you should never write it just like this, but I'm just going to leave it like this because it's the only part that this d dx acts on. What does d dx do? It brings down a k sub x, the x component of k. What does the y derivative in here do? So this is still, we're just solving this, right? Equals this plus the y component, e naught, e to the I. Now this is the ky. Y. Again, each of these e's have all three components in them plus time, but I'm just ignoring the parts that aren't going to matter with this derivative. So we get, and this is the, remember, once we take it, because this is an exponential, once we take a derivative, we get the original thing back. So this is going to be e naught e to the I kx x. I'll just say k dot x or whatever. Plus, this is going to bring down a ky plus kz e to right? Because the third one, the dz of here, of this del, is going to bring down. So if you don't remember why I'm writing, if you don't know why I'm writing these derivatives here, just look up what del dot, what the divergence means. This is the divergence of e, right? Now, this is actually just the dot product. Yeah, oh, sorry. No, that's right. This is actually just the dot product of k with our original vector e, right? This e here. And this, right, because e is this whole thing. Each of these is e. This is just the dot product of k with e, because we're dotting each of the components together. And we actually get that this, remember this was equal to 0, because there's no charges. So if k dot e is 0, that means that k is perpendicular, is 90 degrees to e. Now we don't know what, they're in 3 dimensions, so it just says coming 90 degrees. We don't know which orientation it's in. But what is k? Remember, let's think back. Okay, why do we even do this? What is k? K is the wave vector, and it points in the direction that the wave is moving in. So remember, right, this is just from the wave section, when we have an e to the I k dot x, that k tells us the direction that it's moving in. Because remember, when we had the refractive index, we had to remember what k was, and k could have this imaginary part, which means it decays. So we'll get to that in a minute too. Again, even though we've talked about that before, but I just want to, go over it again. So k is the direction the wave is moving in. What this means, because the divergence of e is 0, and e is given by this wave equation, the wave can't travel, the wave has to travel perpendicularly to e. So let's think about what that means. Remember divergence, if you watch those videos by 3 Blue 1 Brown, which if you haven't watched those, you should definitely watch those. It's up in the Slack channel somewhere. But I posted, I think it's called like fluid flow meaning of divergence and curl or something like that. But it gives you an idea of like divergence means a vector field that's emanating from a point. And curl, we could talk about curl in a minute because we haven't used it yet, but divergence is this, us coming in from a point. The fact that it's 0 just means that there's no points that emanate charge here. Sorry, emanate electric field, which are called charged points, which is fine, that makes sense. But if that can't happen, if we don't have any charges, so it can't come from a point, we must have that the direction the wave is moving in can't, like the wave can't move outward from anywhere, if that makes sense. If this is sort of my, okay, I should have said this at the beginning. This is sort of my intuition of why this makes sense. You should come up with your own if this doesn't work for you. But I'm just trying to say why the divergence of an electric field being 0 means that it must be moving perpendicular to the way it's actually oscillating. Because if it wasn't, if it was oscillating up and down, right, meaning at this point it's going up, and if it was moving upward, it would kind of indicate that there must be a source down here that's pushing it upward. Does that kind of make sense? If it doesn't make sense, that's fine. And it's also not really a great explanation, but sorry, I just want to get to the other thing, which is the fact that we know that this is true. This is just true this is always true. For just anything, it doesn't have to be when there's no charges, but this is always true. The curl of E is the change in magnetic field over time. This is not 0, okay, because there is a magnetic field. And because the curl of E tells you, now we know that the derivative of, we know that this acts like the derivative, right? Del is just this is now a vector of derivatives. and we take the cross product with E, well, remember, when we take derivatives of E, we get K times E itself, and this is actually going to act like this. Now, these are not equal, but I'm saying the direction of this is the same as the direction of this, because remember, taking dels of E gives us something in the direction of K, right? And so taking del cross E would give us something in the direction of K cross E. Does that make sense? Because the del, the way I did this, is the same. It's not going to look the same. We're not going to add them, but it's still going to be in the same direction. So this derivative acting on E is going to end up giving you something in the same direction as K cross E. Because when you take the derivative, you get the vector field back itself, right? So K cross E is the change in B over time, but remember, the change in any of these E and B over time is just the same as, it's the same direction as, like the electric field is oscillating over time, but it's not oscillating in a different direction. It's oscillating up and, if this is the X direction, BE is oscillating in the X direction, right? So E is in the X direction, is in X, right? But therefore then dE dt is in X. This is just how waves work, right? dE dt is in the X direction. You can kind of tell that's true because in the wave formula, this omega t part doesn't have any spatial components. So the time evolution is not changing the orientation at all. That's just what that means. This K and omega are separate. Anyway, so this means that to find the direction of B, all we need to do is find the direction of K cross E. Well, we know that K must be perpendicular to E. So let's say E is in the X direction. Let's call K is in the Z direction. And I'll just call this direction Z. Now it's 90 degrees oriented from E, which is this way. So that's fine. Now you could pick any, but that's fine. Now obviously we know by cross products, B must be in the Y direction, but it actually it's not obvious if it's plus or minus Y. So if we do K, which is Z, so I'm using my right hand, K cross E is Z, which is up. So the out of the board direction is the positive Z direction, but because there's a minus sign here, oh, sorry, no, then we're right. B is sticking up out of the board like this. So B, which is, you could also, sorry, it's also H. It's the same direction as H. Sticking up out of the board. The minus dBt is the reason it's minus is because over time it's going to decay from a maximum, right? So that's just telling us which direction it's going to decay because there's a minus sign here. So it just means it's going to decay from a maximum. So at a maximum, it's out of the board. So the B field's out of the board. Let's actually check this because I know I sound very uncertain. It's because I slightly am. Let's check this. So if I call, let me erase this. Actually, let me just erase all this. We know that the Poynting vector, S, tells you about the power. It seems like I'm changing topics, but I'm not. Is equal to E cross H star. We mentioned star just means complex conjugate, so this is real because this is going to be power per area. So if you want to find the power per area, you could just take the maximum value of the electric field, which is going to be the value of E naught, right? And I erased the wave, but it's that, times the maximum value of H. And if you take the modulus, meaning if they're a complex number, you just take the modulus. It would just be this. You don't need to take any more complex conjugates. This will be the power per unit area. Anyway, the Poynting vector is called Poynting. And what's nice about the Poynting vector, it's named after a guy named Poynting. So it doesn't have anything to do with the word point, but it literally means, it actually does point in the direction of the wave, which is really convenient for Poynting. I wonder if he was inspired by his own name. But anyway, so S is in the same direction as K. This means parallel. So S is in the same direction as K, and I drew before that I just erased. If K is in this direction and E is in this direction, what direction is B going to be in? Well, we know that if S, so S, this is equal to also S. K is moving in this direction, E is going up, so we know that E, so I'll do E cross H, it has to be S. So I know S has to be this way, E is up, and so it is correct. H does have to be out of the page like this. So now we have E cross H is S, right? And it works because this is my right hand, and I'm doing A cross B is C like that. My thumb is the result in this order, whatever this finger's called, index finger, middle finger. That has to be the right order. If you do it the other order, obviously you'll get the minus answer. So the point is that we've confirmed this, and we've confirmed what I just said. It's a little confusing because I probably shouldn't have said it that way, but I was saying it with the minus dB dt is in the same direction as B. And this is just because, again, from a maximum, it decays over time. And we can see that by the wave equation, there's a minus sign with the t. Anyway, so the point is that that this is the directions associated with a electromagnetic wave. There's an E and an H. They have to be parallel. They have to be perpendicular. They have to be perpendicular, and they're moving in a direction associated with the pointing vector, which is the cross product of them, using the right-hand rule, of course. And that S is also in the same direction as the wave vector K, which appears in the exponential of when you write them. Now, for basically ever, and for every class you ever take about this, and electromagnetic waves, you'll never write the H wave as an exponential. It totally is. So we can write E is E naught, which is a vector, times e to the I k dot x minus omega t, okay? This is E. We can also write H equals H naught e to the minus blah, blah, blah. It'll be let's see, how would it be different? The phase would be off. Anyway, it'll be slightly different, but we almost never write that because if you know this and you know, remember K is a vector too. So if you know E as a vector and you know K as a vector, you can actually totally compute H because it's sort of determined by this, right? And so you actually never really would write H because it's sort of overdetermined. You wouldn't really. Also, polarization. So we should talk about this. If this is the X direction, this is the Z direction, and this is the Y direction. This light here, where the electric field goes in the X direction, would be called X polarized light. If we rotated this like this, so the electric field was going in the Y direction, the magnetic field was going in the, I guess, the minus X direction, and the K was still in the Z, that would be called Y polarized light, okay? And of course, it depends on your coordinate system. This, either way, it's called linearly polarized because it only goes up and down. You can also have it move in a circular path, meaning it's moving up and down in the X direction and up and down in the Y direction. Sorry, up and down the X direction, up and down the Y direction, but at different phases. And that ends up looking like a spiral, and that's called circularly polarized light. And you can have it go clockwise or counterclockwise, and those are two different polarizations. That's how 3D glasses work. Actually, it's not how 3D glasses work. 3D glasses work by linearly polarized. The point is that the direction of polarization is defined as just the direction of the electric field. So I'm just saying all this to tell you that why do we keep talking about these three pieces, these three perpendicular vectors, and we only ever write anything for the electric field? And the reason is just because the electric field is sort of how you define everything because it's a little easier to measure than the magnetic field. And it's also H is determined everything about you want to know about H is determined by E and K. And E and K are very easy to measure. K meaning sort of like S, the direction of S. And so we just define everything like the polarization by the direction of E. So whatever E is doing is called depolarization. I was going to say 3D glasses, of course, work by giving you light waves that normally if in sunlight and most lights that you would just use for normal purposes are polarized sort of randomly because when they're emitted, they're just sort of random in random directions. They might be circular, they might be not. Sunlight is randomly polarized, but there are certain processes that you can find in nature, or you can create them on purpose in a movie theater or something, where you emit only photons with a certain polarization, where, for example, you only want vertical polarization, which means that if you put the glasses on and you're standing up, assuming you're not leaning down sideways or something, then light that comes up and down is maybe lets through light that the electric field is oscillating up and down, but not laterally. And of course, if you just turn the glasses sideways, you'll get the opposite effect. And the reason that so that's used in movies and stuff, and so they can give some things to your left eye and some things to your right eye if they just make the left eye vertically polarized and the right eye horizontally polarized. Sunglasses also are called polarized sometimes because, and I mentioned in nature, it's slightly different because in nature, some processes like seeing, like if you're driving and you kind of see out onto the road, reflections can reflect more certain polarizations of light than others. So if you're seeing the sun sort of ahead of you on the road, if you're driving, so here, let's say this is you in your car. I can't draw a car. So let's say this is your, and this is the sunset, and you're driving or walking, I guess, and this is going to emit random light, but the light that reflects off of here is actually going to be mostly polarized light, vertically polarized. Yes, I think I might have this. It might be horizontal light. It's one or the other, vertically polarized light. And so sunglasses are made with one or the other, vertically or horizontally. I can't remember which is which. One or the other polarization filters, such that it looks pretty much the same because, again, the sun emits mostly random light. So if you look at most things, it'll look fine because it's sort of random and you're just getting maybe half of it or something. And that'll just look like normal sunglasses. But if most of the light from a reflection is going to be horizontal or vertical or whatever, and it's blocking those, it's only letting the other ones, you'll actually really dim these reflections because you don't want, when you're driving, to see this glare off the... So it'll reduce glare a lot more than random. So it'll reduce random light by maybe 50%, but it will reduce glare by maybe 80%. So that's like why they use polarization for sunglasses. Anyway, you can look this up. If you look up the Wikipedia page for polarization, they show some really cool... There's like a photo. I might have been. The last time I looked was like a year ago. But there's a picture of like a window like a picture of someone's window, of a house with a window, and the window looks just completely white because it's just sunlight reflecting off of it. But then they show through a polarization filter, and you can just see it looks like there's no glass at all, and it's just because they say that the light reflecting is very, very polarized, and because reflected light gets polarized a lot more than random sunlight. You can filter it out very easily by just choosing the right polarization filter. So anyway, sorry, that was a big tangent. I should mention that, so for the Poynting vector, this symbol, this, is the time averaged power over area, or intensity, I think you'd call it, but I'm just going to write this. Now, why is it... Now, this bars here mean averaged, okay? This is just... Sorry, it doesn't mean average, it means magnitude. Because S, the actual Poynting vector, remember I said it's E cross H, those oscillate over time. So this means the magnitude of the value. These bars in here, these bracket things in here mean time averaged. So the point is that we don't actually care about the fact that the waves go up and down and up and down. We actually just care about over time. So in other words, if you take it over a full period and then divide by 1 second, if let's say a period is 1 second, if you take the power you've received over 1 second, it's actually going to oscillate up and down because it's actually going to kind of go like, well, it's never going to be negative. It's actually going to kind of go like this or something, and it's just because of the way the cross product of the two things work if they're in phase. Also, it depends on what phase they're in, because you could have the magnetic field be at a different phase than the electric field. But anyway, and so if you just take one full period and then you average it, you'll get some value like this, and this will be the time average value. And then again, you have to take the magnitude because it's in general a complex number, so you take that. So this is the time average power per unit area. So if you want to do anything, this is the symbol they would use. I'm putting another box around it, but this means time average, this means magnitude. So anyway, that's what you'd actually compute if you wanted a value for a real number value for the time averaged power per unit area. Okay. Now, what else was I gonna say? Okay, I just want to mention real quick too about the index of refraction because I didn't really go into that last time. The index of refraction, of course, is just one way to write it is C over V. V is the speed of light waves in that material, and C is the speed of light in a vacuum. But remember, from the wave equations, you can actually derive these, and we'll get that N is actually equal to mu epsilon over mu naught epsilon naught. And the reason is because that's C is 1 over mu naught epsilon naught square root. Sorry, C is 1 over square root of mu naught epsilon naught. V is 1 over square root of mu epsilon, right? Now, of course, if you're in a vacuum, v is going to be equal to c, and this is going to be 1, and etc. But, so that's this, and we can actually write this as, and they have a way they write it, which is mu r epsilon r, where mu r is just mu over mu naught. It's called the relative permittivity of free space. Epsilon r is epsilon over epsilon naught. This is called the relative permeability of free space. It's just a little notation thing. You can see why writing these knots and stuff everywhere might be a little confusing. So in other words, n is just equal to this. And remember, we said that epsilon could get a complex thing. Remember, we said that you could get something like this. And mu could have the same thing. Now, when we divide them, remember, mu naught and epsilon naught don't have any complex components, but when you divide them, in general, they could still have complex components. And so we actually get that n tilde is the complex index of refraction, which is still mu naught r epsilon r, mu r epsilon r, which in general could be n plus I kappa, okay? N is just the real part of this. So n is the real part of this. So, I mean, obviously, because I'm writing it as something plus I something, this is by definition the real part of this, and this is kappa is by definition the imaginary part of this. This is not k, remember, this is kappa. It's a Greek letter. N is still just c over v for a real number. These are all real, as in everything in here is real. Here, we're allowing these to be complex, okay? So these have complex mu and epsilon, and this is called the extinction coefficient. And it's because, let's say we go back to, remember our dispersion relation? So a dispersion relation is like this. It was like, I think it was this. Remember, basically it's the thing when you do the wave equation and you plug in a solution. So dispersion, so let me write that instead. Dispersion means write wave equation, plug in solution. Okay, let me see if you can see that. Okay, sorry, I don't know why this is like, whoa, sorry. Okay, well, it says dispersion. I'm sorry, there's no way for me to... Okay, anyway, sorry, I won't write over the end now. Actually, let me just do that. Oh, okay, there we go. So dispersion relation is where you just write the wave equation and then you plug in the solution and you get some relation between omega and k, and it depends, and this is how we got the speed, remember all that stuff, okay? So this is the dispersion relation. We can actually write this now as n tilde over c if we have in general imaginary parts of these things, right? And now we can write the wave, if we plug it back in, I'll make E naught is the same, e to the I, and now we have n tilde over c, remember again, n has complex parts, omega x minus omega t. And then this becomes, if we just plug in n tilde, we get E naught times e to the minus kappa omega x over c, e to the I n omega x over c minus omega t. Okay, so what this means is that you have this part, which is literally just an oscillating wave. N is the coefficient, n is the index of refraction, the regular index of refraction. N over c is just, n over c is 1 over v. So you get a v on the bottom. Omega over v is k. Yes, so anyway, this is just kx minus omega t. I just plugged in the other side for k. So this is just the wave by itself, okay? With the real part of k, I should mention. This is a decay. This has no time in it, which is good because we don't want the decay to depend on time, but it does depend on distance x. And this is a kappa now. So I'm sorry, this is, I'm gonna put a bar. I'm not gonna do that, no. That's more confusing. This is regular k vector that goes here. This is kappa, which is the, I just erased what it was called. What was it called again? The extinction coefficient. This is called the extinction coefficient. So in other words, this is going to give you, this is all sort of review from what I said last time, but I didn't use this notation, which I think is actually good to go through this. And this gives you the thing where you go like this, right? And this oscillation is given by this wave, and if you look at sort of the magnitudes of each, the magnitudes of the peaks and the troughs, right? You'll get this equation here, right? Because this tells you about the magnitude. Basically, you can call the amplitude of the wave not just epsilon, or not just E naught anymore, but E naught times this decaying thing. So the amplitude decays, and then you just get a normal wave oscillating in the middle here, okay? So this is just like the damped oscillator. It's actually a little easier than the damped oscillator because we don't have these silly little, like, the frequencies don't change and stuff like that, because it's light. So light always has the same frequency no matter what. The wavelength can change in different materials, etc., but the frequency can never, ever, ever change, because that's sort of intrinsic to the photons themselves. So anyway, this is a non-conducting material with a complex index of refraction, which comes from a complex mu and epsilon. And to figure out what this n is, in other words, to figure out what n and k are from mu and epsilon, you might have to take a square root. That's why he did the thing where he took the square root of I in something. Remember, he was talking about this, and you're probably thinking, why are we talking about math? The reason is because if epsilon is like something plus I something, if epsilon r is something plus I something, or up here really, it's something plus I something, it's all in the square root, and so you'll need to take a square root of I, and so we write this as, I'll just go over it again, I is equal to e to the I pi over 2, right? If this is in polar coordinates on the complex plane. And now the square root is easy because square root just means to the 1/2 power, and now it just becomes e to the I pi over 4. So that's it. And yeah, so that's how you can go if they give you, for example, if they give you a mu and epsilon that are complex, multiply them out, obtain the relative versions, or leave them like this, it's fine. I mean, you just divide them anyway. So I guess you have to do this no matter what. And you get a complex number under the square root. We can use this trick to get the actual square roots in terms of a real and imaginary number. Remember this, no matter what, even if we put i's everywhere, this is going to be something plus I something, right? No matter what. So it just might be a little hard to find. But then once we get this, we can plug this into the dispersion relation, which has, and then when we plug the dispersion relation into the, When we plug the dispersion relation into the wave equation, we just obtain a decay part, which is proportional to this, and a wave part, which is just the normal wave part. But it looks funny because we've plugged in something. So anyway. Actually, I'm sorry. I should have some square roots somewhere. Okay, look in the notes for this thing. I'm afraid I didn't take I should have taken a square root here, and this should be a square root or something. Okay, look in the notes because I don't want to redo it and then do it wrong or something. Anyway, look in the notes. There might be some square roots you need in these parts because I think we should have taken a square root here. So anyway, but the idea is the same. The idea is correct. It still decays and it still has the original wave here. That's the point. Okay. So let me see. All right, so now that we're going to talk about the boundary conditions. So we're going to talk about the idea of, there's two ideas you need to use for the boundary conditions. And using those two ideas, you can get the boundary conditions for E and H. Or sorry, I'll just say for the electric and magnetic fields. In some cases, you use E or D, some cases you use H or B. And the point is that if we draw a boundary here, and now that we're not always going to have the same mu and epsilon on each side. Okay, so this side has mu and epsilon, this side has mu prime and epsilon prime, okay? I'm not gonna actually use these in the things, I'm just saying that, you remember in general, the point of this is that they don't have to be the same. What we can do is, for the first boundary condition, is we're gonna relate the tangential component of E in 1, I guess I should call these 1, and these I'll call 2, okay? So mu, there should be a comma, but I don't want to write a comma, it's going to be confusing. But so E tan 1 and E tan 2, okay? This means 2, not squared. So I want to relate these two electric fields. In other words, if what's going to happen, I mean, look, okay, forget about the waves. What's going to happen is waves are going to come in and go through. But imagine we just have an electric field here and it propagates into here. What is it going to be on this side? What we can do is take a loop. So these are all going to be about loops. So what we can do is take a loop and we're going to use this equation. Sorry, we're going to use this equation. And if we integrate this over the area of the loop, so if you feel like, if you're sitting there thinking, I couldn't have figured out how to do this, even though I know Maxwell's equation, but I wouldn't have figured out why to integrate over A and what am I doing? I totally believe that's totally fine. You're not supposed to be able to derive this just from, you're not supposed to, they're not going to ask you what is the boundary condition, derive it from first principles. I mean, they might now that you've seen it, but they wouldn't if you didn't see this. They wouldn't ask you that. That's very hard. But you should follow this and understand it, and probably write it down. At least write down the result somewhere because you might need to use it. But just keep in mind why this is true, and the fact that we're not actually using anything new here. We're doing different things, but we're not using a new technique. We're using divergence theorem, Stokes theorem, and Maxwell's equations. That's sort of the only thing we're doing, okay? This here, we're going to use Stokes theorem to turn this into a ds of E times dl. I'm trying to keep my personal notation consistent. It might not be the same as his, but of course you should be able to relate them. So by Stokes theorem, the integral of the curl of something over an area is the same as the integral of that thing over the loop around it. So now this is area A, and the loop is L, right? A little piece of the loop is dl, which is a vector like this, okay? And this side is and I'm going to leave it because it's just the area integral over the change in the magnetic field over time, okay? Now what I'm going to do is say that this is a loop integral around this loop, but because it's a rectangle, it's just going to equal to E dot, so this is going to equal to E dot, I'll call this L1, L2, L1, L2, because this is the length. So we get E dot L1 plus E dot L1, because there's another, so there's a 2, plus, now in this case, okay, actually, it is going to be a little more complicated. I have to say, what we're going to do is take L1 to go to 0, okay? What happens when L1, that means that we're going to take this to go to 0, because that's fine. All we care about is the tangential electric fields right at the surface. We don't actually want them away from the surface. So we want to take L1 to be 0, but if L1 goes to 0, what does that mean for the area? The integral of the area of anything, this doesn't depend on the area at all, right? This is just dB dt. dB dt is whatever it's going to be. So in other words, this becomes the integral over the area of some constant. But if the L1 goes to 0, the area is just 0, right? What's the area of a rectangle with 0? Well, that's just 0. And if we integrate a constant over that area, over an area of 0, the answer is going to be 0. So it's 0. So, but we're not done. We didn't find anything yet. That says that this is 0 around this loop when L1 goes to 0, okay? So now how do we use that to find the E's of these two pieces? Well, this E dot dl of a closed loop is going to be E dot dl1 plus E dot dl2 plus this. But remember, these went to 0, so we actually don't even need to consider it. So what this is going to be equal to is E, and let's say I'll start with this one. So we're going around, because it's a closed loop, we have to choose one way to go around. So E tan 2. Now tan is important because I'm only considering the dot product of E. So E could be any direction, right? But E tan is going to be the tangential component along the surface, right? And so E dot L2 equals E tan 2, right? Because it's just the component of E. I shouldn't have written tan. There's just E1 and E2 in both of these regions. But E2 dot L2 is E tan 2. I'm sorry, where I'm putting the 2 is really not consistent. Don't read anything into it. I'm just trying to put them somewhere. E2, I'm sorry. I know this is like incredibly annoying for you. E2 is an electric field over here. E1 is an electric field over here. What we need here is E2 dot L2. Therefore, we get E tan 2, okay, times the length, L2. It's not a dot product anymore. We've already done the dot product by getting tan. And then when we go this way, well, E1 was still going up. We have to choose one direction for them. So this is actually going to be, so E1 dot L2 is going to be minus I'm sorry, let me write this over here. E tan 2 L2, right? Minus E tan 1 L1, right? Because E1 is going up and L2 is going down, right? Because we're going around the loop. And then that's the only piece. Now this was what? This was this closed integral, which is 0. And therefore, E tan 2 equals E tan 1 because, sorry. And these cancel, right? You can just divide by L2. And we get, the first boundary condition is that E tan 1 equals E tan 2. Okay? I'm sorry, that was like all over the place. I hope you followed that. All we used was the fact that all we used was this Maxwell's equation. Then we did Stokes, then we just took the integral of both sides over an area A, which I just made up, that goes across the boundary. Then on this side, we recognized that, then on this side, we took Stokes' theorem to get E dot dl over a closed loop, over the boundary of that area. So that's fine. That was going to be equal to this thing, which we don't know in general, because we don't know anything about the magnetic field. But we said, what if we take our closed loop to have a width of 0? Then this closed loop integral only has 2 parts, because normally it has 4 parts because it's a rectangle, but 2 of the parts are going to be dotted with something with 0 length. So 2 parts went to 0. The other 2 parts were given by this, where the dot product turns the e's into tans, which means only the components along the surface, okay? And this side says that this, which doesn't depend on the area, is integrated over the area, but the area is going to be 0. So if we integrate some constant over no area, we get 0. So we know that this equation was true. That's how we get to this equation. And this equation, we know that E dot dl became E2 L2 minus E1 L1, and therefore that was equal to 0, and so we get E tan 2 equals E tan 1. Notice that this doesn't tell us anything about the components of E perpendicular, normal to the surface. So let's do that one. That one is, actually, sorry, before we do that one, I'll just mention what you'd get for the magnetic fields. For the magnetic fields, you use the exact same thing, but instead of this, we use H, and here we have D, so this is just another Maxwell's equation, but we also have minus J for the current density. Actually, it might be plus J. I think it's plus J. Then we do the same integral, so I'm not going to write it all, but we do the same integral. The only difference, everything's identical, and so we end up getting H tan 1 equals H tan 2. This is exactly identical for H. The only thing we have to worry about is that there's another term here called the current density. When we integrate the current density over the area, we get the current flowing along the surface. Even if we take, remember in this part I said that we take the area to be 0 by squashing the rectangle like this, like that. And of course this was this doesn't matter because this doesn't depend on the area. But if we take that the integral over the area of the current density on the surface, even if we take that to 0, we still have a piece, which is what if there's a current right along the surface? The current is sort of one-dimensional, right? Because it can be along a single line. So if there's current along the surface, this is actually not 0, and this doesn't hold. So this is only true when J is 0, meaning that there's no current when J on surface is 0. Remember, this is all supposed to be a surface between, usually it's like vacuum, like outside vacuum, and then like glass or something, some material or water or whatever, where we talk about electromagnetic fields going into it, right? And then changing properties and stuff. Good. So this is only true, we had to use this because there's an extra term in this Maxwell's equation. We had to use the fact that J, the integral of the current density over this area here, has to be 0, okay? Which just means that there can't be current flowing on the surface. This is always true no matter what, because there's never magnetic field flowing on the surface. Doesn't make sense. So, well, anyway, yeah. And so, yes. So that's the first one. Now, these are all the tangents. What about the normal components? Okay, so I'm going to redraw this. So the normal components we're going to get at using a Gaussian surface. So the normal components, remember, are the components that go like this. This is called E1. This is E, sorry, I can't. This is E2. And we're going to use a Gaussian surface, right, as we did before. Let me turn my page. Actually, we're going to use D. And so if we use Maxwell's equation that this is why I want to use D, because I want to say D dot, you'll see why in a second, why I'm using D. It's actually the same reason as why I used H in the other one, I just wasn't like explicit about it. E dot dA equals Q enclosed. So here's the reason I want to use D and not E, because if I used E, all I would do is put an epsilon naught at the bottom here, or an epsilon at the bottom here, but these are different surfaces. So that means when I do my integral, I have to I can't just say it's equal to this, because I have to somehow keep track of it doesn't even make sense if I say E over here, if I enclose a region where some of my region has a different epsilon than another, how can I write this side as Q over epsilon naught? So it's actually really hard to do this Gauss's law equation without using D, unless you know you're in the same region all over, which is in the other cases we were in where we used that equation. So anyway, so we have this. Yes, and now we say that we're only considering the normal components. So the integral, so this is our Gaussian surface. It has area A at the end. So dA is perpendicular on both sides, right? Like that, like going out. And the other region is all going to be canceled to be 0. And so this is actually just going to become A, which is this area, times D1, minus A times D2. Remember, it's minus because D2 is going to go this way, right? We have to consider the same direction in both cases. So D2 goes this way, A goes that way now on this side. And so we get this, so A times D1. And now I said that they're perpendicular only, but if you wanted to consider them in a general direction, well, the dot product of a general D with A is only going to be the perpendicular component. So now we can sort of write perpendicular or normal. The way they'd say it is normal. Normal means perpendicular, of course. And this is going to be equal, now what's the charge enclosed by this region? Right, we can even take this to be 0 if we want. It would just say that's what is the charge on the surface, right? Well, you might think, we just say 0, and then we cancel the A's, and we get D1 normal equals D2 normal, okay? Now that is basically true. That's fine. That's what we say. This is just fine. However, there are materials that we've talked about that have charge enclosed on their surface. Conductors, for example, if we have a conductor with a net charge, the charge all goes to the surface, okay? Then we actually can't do this. The electric field is not continuous along, the normal component is not continuous along the surface if there's a charge on the surface. So this, we have to, again, just like in the last one, remember we had to say there's no current. This one we have to say if no charge on surface. Okay? And then also note that, just one more quick thing. So anyway, this is a big caveat because this is not true in general. You could have other situations where you have charges on the surface. E1 normal is equal to epsilon 2 over epsilon 1 E2 normal. I'm just writing this because, remember, we used D's this time and I gave a reason why, which had to do with the fact that there's different epsilons on this side, which is kind of annoying. So if you absorb them all into D, that's fine. But if you want to turn it back into E, it would become this. Epsilon 2 over epsilon 1 is the ratio between the epsilons here and here, right? So you just keep that in mind, that H and B and then D and E are, of course, equivalent. You can just always replace them wherever it's convenient. And in this case, it was much more convenient to use this whole thing with D's as opposed to writing, I mean, I don't even know, you can't even do it really if you divide by epsilons, different numbers of epsilon each side, right? What is charge enclosed over two different epsilons? I don't know which it is. So, so this is the actual normal condition relation. You normally write it like this. This exact calculation works exactly the same in magnetic fields. You can use B, and you get basically the same exact thing with mu's instead. This is all works perfectly, except instead of Q enclosed, you get exactly 0 for B because there's no magnetic monopole, so you don't even have to worry about this in the other one. So there's an H1 where the H perpendicular is equal to H perpendicular. Maybe there's mu's or something. Again, I would look it up and just write them down. But the point is that those are the four boundary. We got four boundary conditions. We got electric field perpendicular and electric field parallel. Sorry, I'm using different. Sorry, this is what I would call normal, and the other one I call tangent. You could also call this perpendicular, and you could call tangent parallel. It just means parallel to the surface, right? The surface that goes like this. And the same ones for H and B, or equivalently B. So for H, you can get that and we basically find that they're all continuous, except for these minor things like there's no charge and there's no current on the surface. If that's true, if those are both true, which they don't have to be true in conductors, but in most, if normally they'd give you a problem where you don't have to worry about that. And now, this is the last thing I'm going to talk about, and it's going to be basically, I think he says specifically, only know this qualitatively, which is perfect because it's very hard. So what, and the question is, what it talks about is electromagnetic fields at surfaces. So this is, I'm going to draw this diagram. It's drawn in the notes and it's drawn in the book and stuff. Okay, so this is 3. So the wave came in like this, went through and got reflected, okay? Remember when we draw the electromagnetic waves, we have to draw the electric field, the magnetic field, and the K. Now K, oh sorry, that's wrong. When it leaves, of course, it's going this way. K reflected, E reflected, H reflected. Okay? Now, remember what we learned about parallel E's. So first of all, K tells you where the wave is going. So K is clearly going in. Then it gets some of it gets transmitted and some of it gets reflected. Okay, it's not. Some of it gets transmitted, some of it gets reflected. The sum of these two magnitudes. Remember, these are all vectors. But remember, in all these vectors like EI, we get EI naught times e to the I, right? This is the magnitude of the vector, right? So this is the part where if you add up these two, you should get this, right? Because if you take the incident one, the electric field just gets split into two pieces. So if you add these together, you'll get this, okay? So that's sort of obvious. It's also true that if you add the H's together, if you add these two H's together, you get this, but it's a little bit different because this is actually going in the opposite direction. I'll talk about that in a minute. So we get, I'll just write it as EI is going to, of course, be equal to E transmitted plus E reflected. And H incident is going to be equal to the same thing, but because this is in the opposite direction, and we'll talk about why it's in the opposite direction in just 1 second, we get HI is equal to H transmitted minus H reflected, okay? So I don't think you have to know the equations, but just know what's happening here. Something's going in, it gets reduced. I really should write these as like reduced, right? Because they're less than this one, and this is like much bigger. So E parallel stays along the surface as we showed. We showed that E parallel keeps in the same direction along the surface, right? But when it reflects, K of course has to go the other way. And if E parallel is the same, we only have one choice of what H is by the right-hand rule. If we have here, we have E cross H has to be K, right? So E cross H has to be K, which is good, right? Here it's the same thing. Everything goes the same direction. But here we have E cross something has to be K this way, but H therefore is going down. So you might think, well, why is that the case? Why does H have to go like down now? Well, remember, H is actually going into and out of the board everywhere. All that means that's happening here is that instead of, it basically got changed phase by pi. Okay, because remember, changing a phase by pi just means that you negated the whole thing, right? So when we say it goes into the board, we just mean that the positive part of the phase goes into the board. But it doesn't mean that nothing like really different happened. It just got changed by a phase at the reflection. And that's a thing that happens. You can look that up if you want. Phase change by reflection of electromagnetic waves. And we know it must be true by E and by the boundary conditions of E, so they all have to be like this, and the K reversing in sign, right? And we must get this H reflected. Now you can actually draw this, if you prefer to draw it another way, you can actually draw it where the phase change affects the E's, and that would be totally fine too, and you'd actually get the E change of sign, but I'm not gonna worry about that. We don't have to think about that anymore, but you can look that up if you want, because again, the direction, it only really tells you about the phase, because again, if you just delay, essentially here you're getting the magnetic field gets delayed by a factor of pi, which makes it, and if it was like on its way up here, it's going to be on its way down here, but then because it oscillates, it's going to go up and down. So anyway, the point is that they all oscillate in the same direction everywhere. It's just that you get this one change so that the right-hand rule can still be satisfied. So anyway, that's pretty much all about this reflection transmission thing. Yeah, so anyway, and this is the magnitudes, you can look these up. You can also check these with the PowerPoint that he posted, because I hope I got the signs right. I think I did, right? But anyway, just double check. If I had anything wrong, let me know, and I'll correct it for everyone. But yeah, so anyway, good luck. Let me know if you have any questions. I'll post the homework solutions from someone who's written them very well. And yes, let me know, and good luck.